In the previous video, we looked at how pressure at a point varies when the direction or the orientation changes. And in this video, we're going to look at another question that is important, that how does pressure in a fluid vary when there are no shearing stresses present? And how does it vary from point to point in that field? To do that, we look at this small rectangular element that has been taken out of a sort of fluid at some arbitrary location within the mass of the fluid. And now what we can identify is that because there are no shearing stresses or shearing forces present, then there's only going to be two types of forces that are going to be acting on this element. Either they're going to be the surface forces that are going to be because of the pressure, or they're going to be the body forces. And when we say body forces, what we really mean is the weight of the element. So what we will do is that imagine that at the center of this rectangular element, I designate the pressure at the center as P, which would be the point pressure, so I can designate it as P. So then from here, I can derive what the pressure is going to be on the different faces of this fluid element. So if I was, for example, looking at this z direction, and if I was to find out the pressure that is acting on this face, the top face of the fluid element, then of course the direction of that pressure would be towards the fluid, because pressure is a compressive force. And if the pressure at the center is P, then the pressure at this face would be P plus the change in pressure that takes place as we move along delta Z. So that would be dP by dZ, or partial P by partial Z. And because this variation takes place because this entire thing is delta Z, and we are only moving halfway, because from the center, we're looking at it from the center. So the dimension that we are looking at across which this change takes place is actually delta Z divided by 2, because P is at the center, so the change in pressure is going to be from the center to the top face, which is going to be dP by dZ, or because pressure varies in the z direction, in the y direction, and in the x direction, so then it would have to be partial pressure, so partial P by partial Z, and into, because it has only acted through halfway of the delta Z dimension, so delta Z divided by 2 on this face. Just like that, if I was looking at this lower or the bottom face, then the pressure force that is acting on this bottom face would be the pressure that is acting at the center, so P, minus, because now we're coming in the downward or the negative Z direction, so it's going to be minus the change in pressure that takes place as we move along delta Z. So it's going to be partial P by partial Z. And because we only move halfway, so it's going to be multiplied by delta Z divided by 2. And now remember that because we have to apply a force balance, and right now we've only looked at pressure, so this pressure actually needs to be multiplied by area, because force is equal to pressure into area. So from this definition, this is going to be equal to pressure into what's the area of this face that we're looking at. And the area of this face is going to be delta x, which is this dimension, multiplied by delta y, which is this dimension. So it's going to be multiplied by delta x into delta y. Okay, and then just like that, this face has the same area dimensions, so it's going to be multiplied by delta x, which is this one, into delta y, which is this one. So we get this face. Just like this, if I was looking at the y direction now, in the y direction, the force that is going to act on this side of the fluid element or on this face of the fluid element, again, it's going to be a compressive force because we're talking about pressure, and it's going to be pressure at the center, and because y is positive in this direction, so it's going to be plus the change in pressure that takes place as we move in the y direction, which is going to be partial p by partial y into, because we're only moving halfway into delta y, so it's going to be multiplied by delta y by 2, and then we have to multiply this by the area value, and for this face, the area is going to be delta z into delta x, or delta x into delta z. Delta x into delta z. And just like that, on this face then, this face, you're going to have pressure at the center minus the pressure change that takes place as we move in the negative y direction now, so it's going to be minus now, divided by partial y, multiplied by, because we are only moving halfway of delta y, so it's going to be multiplied by delta y by 2, and then this entire term is going to be multiplied by delta x delta z. So these are the surface forces that act because the pressure on the faces in the y direction and in the z direction. I'm not going to indicate the pressure forces in the x direction because it's just going to make everything a bit too messy. I'm going to stick to that. And the last force that we're left with is the body force. That is because of the weight of the fluid element. And the weight of the fluid element from mg, where mass for a fluid can be substituted as rho v, or rho into g into volume. V is volume, rho is density, and rho g is equal to specific weight, which is represented by gamma. The volume of this cubic element is delta x into delta y into delta z. It's going to be multiplied by delta x into delta y into delta z. Okay. So that's the weight of the fluid element. And now if we were to look at the y direction, this one, we can go ahead and find the resultant surface force in the y direction, which is going to be equal to this force and this force. These are the forces that are in the y direction. The weight of the fluid element is in the negative z direction. So in the y direction, I can sum all the forces, and by doing that, I've got the first term, which is this one, minus the second term, which is this one, because this one acts in the positive y direction and this one acts in the negative y direction. And from here, if I simplify this by simple mathematics, this would cancel out, because this is going to multiply into delta x delta z, and this is going to multiply into delta x delta z as well. Plus minus, they're going to cancel out, and we're going to be left with minus partial p by partial y into delta x delta y from here, because they're going to add up, so, and then delta z. So this is the resultant surface force in the y direction. And just like this, I can also account for the resultant surface forces in the x and z direction, and they're going to be exactly the same except for partial p by partial x and partial p by partial z. And remember, we're only talking about the surface forces right now, so we have not accounted for the body force yet, which is the weight of the fluid element. So we've got these three resultant force surfaces, and now I can actually, because I've got this in x direction, in y direction, and in z direction, so I can express these in the form of a vector. How can I do that? Well, I can sum all the forces as, if this was a vector, sum of all the surface forces would be equal to the sum of forces in x direction multiplied by the unit vector, which is I, plus sum of all the forces in y direction multiplied by the unit vector in y direction, which is j, plus sum of all the forces in z direction multiplied by the unit vector in z direction, which is k hat. And I can just plug all of these in, the ones that we already found, and by doing that, I'll arrive at this equation. And if we look at this term here, the one that is in the brackets, what we can see is that this describes the change in pressure that is taking place in the x direction, in the y direction, and in the z direction. So change in pressure is also known as pressure gradient. So I can actually equate all of this, because this is representing pressure gradient, and I can then represent it in the vector form, and that can be written as del P, or gradient of P. So this I can substitute here. Instead of writing all of this, I can simplify it and write it as del P, and then delta x, delta y, delta z can go on the other side, and because delta x, delta y, delta z is volume, so then it's going to be represented as force, or the resultant surface force per unit volume is going to be equal to minus del P. That's how I can do that. And now that we've accounted for all the body forces, I can move on and look at, we have accounted for all the surface forces, I can go on and look at the body force, which is the weight. And because the weight is in the negative z direction, so it's going to have, obviously the unit vector is going to be k, it's going to have a minus sign next to it, and then I can simplify this, and instead of writing this, I can substitute it by the value of weight that we've already looked at or derived. So I can just substitute that here, and that's going to be multiplied by the unit vector k hat. So now I can go ahead and apply Newton's second law onto the fluid element, and what the Newton's second law says is that the sum of forces, if we're looking at the vector form, the sum of forces, and because we're looking at a fluid element that has dimensions of, that is small and has dimensions of delta x, del y, del z, so the forces on it are going to be a summation of del F, and that's going to be equal to delta M into acceleration. And then obviously we would have to account for not just the surface forces, but the body forces as well. And the surface force is being represented here, and the body force is being represented here. So that means I can just sum those up, and I can write it in this way, and obviously that is equal to MA. Or I can substitute here the surface forces, because I've already designated this entire thing as del P, so the surface forces are going to become minus del P into delta x, delta y, delta z, minus the body force, which is going to be gamma into delta x, delta y, delta z in the k direction, and that is going to be equal to mass. We've already said that it's going to be rho into v. Rho is density, and v is volume, and volume is delta x, delta y, delta z. So I can simplify this equation in this way. And now because we've got delta x, delta y, delta z as a common factor in all of these terms, so those can be canceled out, and this equation can be simplified as this equation. And this is an important equation because now we have a simplified general equation of motion for a fluid, and we can apply this general equation of motion for a fluid in which there are no shearing stresses present, first of all, and we can apply it even to the cases where the fluid is at rest. So this is a general equation that can be applied to any fluid element, whether it is at rest or whether it is in motion. So now we will focus our attention on the special case of a fluid that is at rest, and we will apply this equation onto that fluid element. So we're going to use this same equation, but because the fluid element is going to be at rest now, what that means is that the acceleration is going to be equal to 0. And when the acceleration is going to be equal to 0, then that means that this term is going to cancel out. And basically we can move around this equation now, and del P is going to be equal to gamma unit vector k hat with a minus sign, or we can keep both of the equations on the same side, and then they're going to be both positive terms equal to 0. And in the form of components now, because del P is equal to what we already saw, this term over here, which is equal to partial P by partial x in I direction plus partial P by partial y in j unit vector direction, and plus partial P by partial z in k direction. So from here what we see is that in the x direction, from this equation, partial P by partial x is equal to 0, and partial P by partial y is also equal to 0, except for it's going to be partial P by partial z, which has the unit vector k hat, and this term also has a unit vector k hat, so it's going to be plus gamma equal to 0. And then I can simplify this, I can move this around, and this is going to become dp by dz. And why does it become dp by dz? Because we've already seen here that p no more depends on x or y, and it only depends on z, right? So that's the entire point of taking partial derivatives in the first place, that the variable that you're looking at is changing in different dimensions. And because this is only changing in one dimension, which is z, so then partial P by partial z is going to actually be equal to dp by dz, and gamma is going to move to the other side, and we're going to be left with dp by dz equals minus gamma. And this is an important result because what it shows us is that for fluids at rest, the pressure decreases as we move upwards in the fluid, and the pressure increases as we move downward in the fluids. Also, what you will see is that there is no requirement here that gamma has to be constant, so that means specific weight can vary at different elevations for air or for other gases. And this is a case which is only specific for fluids that are at rest, because acceleration is 0. That is what we are saying for this equation. If we were looking at a case where the fluid was moving, then this wouldn't be equal to 0, and the pressure variation would be a lot more complex. So in this case, we have to remember that we are looking at fluids that are at rest, and the result is that this is the fundamental equation for fluids that are at rest, and it shows us that as the fluid at rest, as we move upwards in that fluid, the pressure decreases, right? This is what we see. As we move upwards in the fluid, the value of Z starts becoming higher and the pressure starts reducing. And as we move downwards in a fluid at rest, the value of Z starts coming down and the pressure starts increasing.